You guys are getting pumped. You're liking this music. I know you are. Oh yeah. Anyway, that's some soul coughing, some circles. Look it up. Anywho, we got our next video. Video number 2, chapter 1. We're going to talk about some things called dot plots and stem plots, and we're going to talk about your socks. So I hope you're wearing some socks without the K. Okay? So we're going to look at some AP Stats Chapter 1 test scores from 2 years ago. 2 years ago? 2 years ago? Yeah, I guess it would be 2 years ago. All right. Now, the main thing you might be wondering is, man, are these percentages? Are these percentages? Because I think I'm going to drop this class if these are percentages. I'm getting scared. These are not percentages. And you know what? This is fake data because this isn't even real. Okay? But let's pretend. Let's pretend that this is all out of, I'm a different color, can't really write white on white. Let's say all this was out of 36 points, okay? So yeah, well, we got some people that did pretty good, right? Got one person over here, 25, they didn't really do so well, maybe they didn't study, maybe they really shouldn't be in this class, we don't really know. Okay, a dot plot is a way to take our data here, and notice this is quantitative data, okay? We actually have real numbers here that mean something. Okay, if we added up all these numbers, we could find a mean, and it really means something, no pun intended. So we have here, the first kind of graphical organizer is a dot plot. And guess what symbol you're going to use for a dot plot? Shock, I know, dots. It's crazy. So we have it can be horizontal, it can be vertical. Typically dot plots you see with a horizontal graph here, a horizontal line. And I've got numbers spread out here. I know that my lowest was 25 and my highest was 35. If I wanted to go to 36 and include what the max could be, that's fine, doesn't really matter. Does it have to start at 0? No, it does not. You can just kind of take that, snapshot of between 0 and 36. You could say, well, really, my lowest is 25, so why would I show 0 to 24? There's nothing there. Okay? Just say, forget about it. We don't need it. There's nothing there, exactly. We need a nice label here to say what these numbers represent. And I have flubbed once again. This should say 2011, not 2004. Anyway, so now all I have to do is take all of these numbers here. And so, at 25, I come over here and I put boop, a little dot right above the 25. It can be, right on top of it, but you want to start it out somewhere. It can be right on top of that little stick there, right there. Doesn't really matter as long as you're going to be consistent about how things move across here. Okay, so if I have two 27s, here's where I want to put my first 27 in the same line, just about, as my 25. But then what do I do with another 27? All I got to do is stack it on top. Okay, 27.5. Well, let's see, 27, 29, that'd be 28. 27.5 would be right here. And you can notice already my dots are a little too big, but that's okay. 30 would be right here, and I've got two of those, so I'd stack them. I got a 30.5, which would go right there, and I got another 30.5. And if I kept doing this and going all the way to my 35, I would get something that looks like this. Okay? And notice there, yeah, now I put 2011. I always mess things up. You'll notice little inconsistencies that I always screw up on and forget. I always think I'm really careful with what I'm looking at. And inevitably, there's something I'll miss here. So there's our dot plot. And it kind of gives us a graphical look at, how the whole class did. Again, we can see, yeah, there's a little cluster up here. There's maybe a little cluster here. We could say maybe these are like the B's. Maybe here's some C's, some D's, and maybe this guy's an F. If I just wanted to kind of chop up grades there, that's what I could do and look at. Now, what we are going to do, and you're going to see this a lot throughout the year, whenever they ask you to describe a distribution, you're going to use your SOCS without the K. Okay? Now, the first S represents the shape. And we're going to look at the shape of this dot plot. And here are 6 main options here. Okay? We've got symmetric, we've got approximately normal, skewed left, skewed right, bimodal, and uniform. So the first thing you might notice, you might say, well, symmetric and approximately normal, they look alike. True. Anything that's approximately normal, you could call symmetric as well. If I can figure out how to spell symmetric, there we go. So approximately normal or symmetric are the same, but not everything that's symmetric is approximately normal, right? because we could use symmetric for this bimodal picture, right? Symmetric means if you were to fold it in half, it would look the same on the left as it did on the right. And this kind of looks symmetric. Uniform, uniform means that it's roughly flat. It doesn't have to be exactly flat. You'll notice there's some little deviations in here, some variance. But again, if you folded this in the middle, the left and the right kind of match up, right? So we could use symmetric to describe a uniform distribution. But bimodal and uniform, those terms specifically, kind of trump you using symmetric. So if you see something that really none of these other 5 things would fit, and it still looks symmetric, you could call it symmetric. There's always some weasel words, not really weasel words, some adjectives you could throw in there. Like let's say something doesn't look exactly symmetric. You could say it's roughly symmetric. That's fine if you want to throw in some adjectives, and you'll see that throughout the class. Okay, now approximately normal, which hopefully you've remember seen something similar to this. Approximately normal just means it has this bell-shaped curve, and we will definitely talk more about normal distributions later. So approximately normal just means you're looking for this bell-shaped curve, roughly, approximately, as you will. Skewed, left, skewed right. Not symmetric, not normal looking. How do you distinguish between the left and the right? Well, it depends on where the tail of the distribution is located. Consider this thing a tail. And if the tail is on the left side, then it's skewed left. And if the tail is on the right side of the distribution, then it is skewed right. That's how I remember skewed left, skewed right. It's where is the tail. Bimodal means you kind of have 2 peaks going on here. Okay. Now, does it have to look symmetric as well? No. You can have something that maybe does this, comes around, and then maybe there's another peak there that doesn't look symmetric. Okay, so you could call this bimodal. And again, uniform just means that it's roughly flat. Doesn't have to be exactly flat, it could be. But you could call, roughly uniform, somewhat uniform, and that would work. So there's our first S for our SOCS, our shape. Now, the O for outliers. The O is going to be somewhat of an optional thing from time to time. Okay? Sometimes it might just be the SCS, but sometimes we get to throw the O in there. Now, outliers are just values that fall outside the overall pattern of the graph. And we will have a more mathematical way of determining if values are outliers. Okay? So just for now, if something looks like it's way out of the way from everything else, we are, for right now, going to consider that probably an outlier. Okay? So it's going to be just a guess at this point. If you think it's too far away, it's an outlier. If you don't think it is, then it's not. So do we think any of these values up here kind of fall outside the overall pattern of the graph? Some of you might say yes, some of you might say no. Some of you might go, you know what? Well, the shape of this looks like looks like this has got more of a tail to it. So this might be more of a skewed left distribution. Now, would we consider the far end of the tail an outlier? Again, some of you might say yes, some of you might say no. And again, later in some future videos, we will talk about is 25 an actual outlier, okay? So let's say yes, let's call 25 an outlier there, okay? It's kind of far away from all the others, but is the 27s far enough away? Maybe, maybe not. Maybe you call them outliers as well for right now. But again, later we will more mathematically show that. Now, center. So we had S, shape, O, outlier, C, center. Now, we have 3 options, mean, median, mode, and I know you've done this stuff forever. Mean is what you would consider your average, right? You add up all the numbers, you divide it by however many there are, boom, there's the mean. The median is also an average, okay? But it's not what we would consider the average. We consider the mean. But median is another sort of average. It's a measure of center. Okay, and the median is the middle number in the data. And then mode was the most frequent number. Now, the only reason why I throw mode in here and I put an asterisk by is we're not really going to discuss mode a whole lot, but mode being the most frequent number in our set of data was 34. And if I kind of draw in a curve to represent this data, then I can see that's where my peak is where the mode is located. And there will actually be times where the mean, median, and mode are all the same number. okay, where the middle number is the most frequent number, and it just happens to be the average of all the numbers. So the median, which I went ahead and calculated for you, is 31.75. There was actually a tie for the median between 31.5 and 32, so I had to average out those two scores there. The mean, which in this case I'm using an X bar, and we'll get more into that later, but that's the symbol for mean is X bar. The symbol for median is a capital M. 31.35, so you can see that these two things are pretty close to each other. And again, we said the mode was 34, but we're primarily going to be using these. And we can use just these two numbers to determine, more than likely, what shape the distribution is. Okay, and we'll talk about that more again later. Now, the last S in SOCS is for our spread. Kind of tells us about our deviation. Okay, how spread out is our data? And we have some options here. We have range, which I'm sure you remember is max minus min. So my maximum number was my 35, and my minimum was my 25. So my data is spread out between 10 points, if you will. IQR, we will discuss later. It is similar to range. They kind of go in the same category. It is called the interquartile range, IQR. And we will discuss what that is. IQR is actually a better measure of spread than range is, and we will discuss why that is when we get there. And then we have standard deviation, which you've probably heard of. It's a pain in the butt to calculate by hand, which is why, thank goodness, we have technology and we have calculators. Okay? So, we did dot plots, now stem plots. So I've got some more. So if I took all my data and I want to split it up between males and females now. Now, on this final exam here, I had some bonus available, and I've got some people that did very, very well. I had 3 males get over 100%. You'll notice, ladies, I'm sorry, no one aced the test. It was so hard for the girls, because girls just suck at math. That's just the way it is, ladies. I'm absolutely kidding there. Females typically do better than males in my AP Stats classes. So females, you kind of have the advantage here. And the females might rejoice in saying, hey, look, there was a dummy guy that failed the test, and there were no girls. No girls failed. They all passed. So here's what a stem plot looks like. We're going to kind of take our numbers and split them. We're going to have a stem, and a variation of a stem plot was called a stem and leaf plot, which you might remember. Okay, so notice what I've done here is I've taken and this is all males and females here. Taken all this data and I've split it up like this. So my lowest number was this 51%. Okay, and I split up the 5 and the 1, and I put the 5 out here. This is what are going to be our stems. And then all these numbers out here are the units digits of all of our percentages, and those were kind of, once upon a time when we did those kind of represent our leaves, if you will, of a stem and leaf plot, except we don't really call them leaves anymore. We just say, hey, this is a stem plot, period, no leaves. So I only had one score in the 50s, and there is my 51. And then I look at my 60s, and I go, all right, well, I had 64, 69, and a 65. And notice I put these numbers in increasing order. Do you have to? No, it just makes it look nicer. Okay, so it's not a requirement. So there's 64, 65, 69. And another thing to notice here is how I lined up the numbers. Notice these numbers are going in perfect columns here, which is very, very important. That kind of maintains, I'm a little bit off there, kind of maintains your shape if you want to kind of look for a shape. Okay, so notice all those are going into place. If you start squeezing numbers in too much, then you start to lose the shape. Okay, so you don't want to take these numbers and really scrunch them in here, and then you won't be able to see that, hey, that's really where the peak of the distribution is. So make sure all your numbers are evenly spaced out between rows. And if I went through and completed all those out, voila, there's my stem plot. Now, a very super important feature of a stem plot, more than anything, is a key. How am I to read this? Does this 5-1 mean 51%? Does it mean 51 out of, I don't know, 200? Does it mean 5.1%? Does it mean 0.51? Does it mean 510? I don't really know. I need something to use as a reference. So what you're going to do is typically use this first piece right here. And you put it down after the key. And then you say equals what that is supposed to represent. And we want it to mean 51%. Do you always have to do the first thing? Could you come down here and do some other random thing in the middle or at the very end? Sure. Knock yourself out. Now, there's a variation called a split stem plot. Okay? And you might look at this and go, I don't know why I'd want to split this. This looks pretty nice. If I tilt my head to the right so that the smaller number is kind of on my left and the larger number is on my right, the shape of this distribution, it kind of looks like, what do you think? Skewed left? It's kind of leaning more towards the right, so it gives us more of a tail on the left end. Now, sometimes when you have a lot of data, okay, let's say instead of there being this many students, that there are 200 students, okay, then you've got all of these numbers that are just really crammed in to 6 stems. And then it gets kind of hard to see what shape that is. Then you might consider doing a split stem plot. So notice the only difference is instead of having all the 50s go in one stem, now I'm going to split it up into 2. And typically you only do 2 stems that share the same number. It's kind of hard to do 3 because how do you split up 3 evenly? How do you take 10% and split it up into thirds evenly? You can't really do it. I guess you could do into, have 5 of them, and so you could have 50 and 51 be one stem, and then the next 5 could be 52 and 53, but then that gets to be just ridiculous, okay? But if you have a lot of data, you might have to end up doing that, okay? So this first 5 represents numbers 50 through 54, and this second 5 represents 55 through 59. Then this first 6 represents 60 through 64, and then we have 65 through 69, etc., all the way down. So what's that going to look like? Notice my spacing, all even out there. So now if we look at this shape, does it still look skewed left? And you might say, yeah, if you just first glance, yeah, it looks like we've got a tail down here. But then some of you are going to start to go, oh, too far. Some of you are going to start to go, you know what? I don't like this. Do I call this bimodal? Now there's kind of 2 humps in here. I wouldn't call it bimodal. I'd still call it skewed left. But this is definitely a con for a split stem plot. If your data is small, if you don't have a whole lot of numbers, then you start to lose the idea of what the shape really is. So you might want to stick to just a regular stem plot. So a pro is, if you have a lot of data, use a split. If you don't have a lot of data, just use a regular stem plot. And then we have another variation called a back-to-back stem plot. Now if I really want to split up my males and females here, okay, notice I got my stems going in the middle, and then I have my 2 variables here, my 2 categorical variables of males and females. And notice, so I'm going to do the females first. And it looks like, stop here, let me throw this up. This just looks like a regular old stem plot. Now the difference is, now I'm going to kind of go backwards with the males, okay? Now I get to read this backwards. This isn't 15%. I get to read from right to left. That's really 51%. And I keep going. So why would we want to make a back-to-back stem plot? Well, so we could really compare visually our males to females. And again, you might say, you know what? The top 3 scores were all male scores. But check this out, ladies. There are more of you that got an A than there's twice as many female A's than there are male A's altogether. No females failed. We had 1 male fail. Okay, so you can really compare those 2 things. Now, one more thing that's missing here is our key. And with a back-to-back stem plot, this is what's going to be important. You're going to need technically 2 keys. How do I read the left side? How do I read the right side? So over here on the left side, here's our first thing for the males. So I'm going to put 1 line 5 because that's what I see, but I read that as 51%. That's telling me I need to read backwards, okay? And then over here for my females, well, here's my first one, right? So 6 line 4, and I read that as 64%. Okay, so you do have to put these keys on here. And again, I technically need to put a key over here for my split Stemplot, which is still going to be the same thing as it was for my regular one. Okay, so keys are definitely important. Now, the last thing is I want you guys to do this Stemplot. Yeah, make a Stemplot. So here I'm setting you up here and describe the distributions. Tell me about the SOCS. What does the shape of this thing look like? Are there maybe any outliers? It's up to you to determine that. The center, again, you could use mean or median. Probably not going to use mode. And spread, you could just for now use range because that's the only main thing you know about. Okay. So over here, I want you to make your stem plot. And if you look at these, again, you might notice, hey, I've got 3 numbers in here. How exactly am I going to make the stem plot? You are allowed to take your data and round it if necessary. Okay. So I will give you a little hint here while you're making this after you watch the video. This 8.28, you may consider calling it 8.3. Just round it to the nearest tenth. And then here's a stem, and here's its leaf. Okay. Now leaves can only be one number. Okay. Again, leaves can only be one number. You can't have a 2.8 and then spread out and do a 3.0 for that guy. I guess you could. It's just not that common to see it. Typically, I would just round these numbers so that you only see the single digits. Okay. So that is it for the second video. Again, I will check this tomorrow in class, so make sure that you do this part. This is kind of like your homework along with the notes, and we will do more with this in class. Adios and goodbye.